Okay, so here's the review. So there are 6 problems, all from chapter 15. Number 1 is we had this topic on the last test, but we're going to do another one here. So this is a line integral. And what we're going to ask you to do is find the integral over a curve of f. This is a field vector dotted with dr. So what I'll do is I'll give you the, and this will be in 2 dimensions, but it could be in 3. I mean, it turns out the problem I'm giving you is 2 dimensions. But there's some field vector and there's some position vector of x and y. And you need to do this calculation. So the whole idea here is that this actually is not a function of y, x and y, it's a function of t. So your position vector is a function of t, so you'll have to convert this to a function of t, and you can do that. Well, what I'm going to do is I'm going to tell you what page problems and which problems to look at, because what I've done is I've just taken them from the book. So it's page 1076, 27 through 32. So look at those problems, make sure you know how to solve them. But it's basically rewriting this in terms of t and then integrating from t equals something to t equals something. This whole thing will be a function of t. You'll take the dot product. Okay. Number 2. Number 2 is from section 4, which is Green's theorem. So Green's theorem says that you can take a line integral and rewrite it as a volume integral. So Green's theorem says that the integral over the curve of m dx plus n dy, and what they're doing here is they're using the differential form of the line integral instead of using the parametric form. And that is going to be equal to the double integral over the region of the partial of n with respect to x, and this is in 2 dimensions, m with respect to y, times dA, which is typically dy dx. Okay, so that's the topic. Again, I'm going to tell you where I chose the problem from. So it's page 1096, problems 11 through 20. So you'll see that I give you this. Then you can get m and n from that. You take the partials with respect to x and y of those, and then figure out what the area is that they're referring to determine the limits. So this will just be a integral involving x and y. It won't be parametric. That's one advantage of Green's theorem. You don't have to make that conversion. Okay, Green's theorem. Okay, so you can look at that. The next section was parametric surfaces, which you need to be able to do surface integrals. And what I've decided to do there is test you on this calculating the area. So page 1106, problems 35 through 42. So what you do there is you can go to page 1102 and see what the area is. So the area of a parametric surface, you take the integral, the double integral over the domain of the absolute value of r, partial of r with respect to u, crossed with the partial of r with respect to v, times dA. So you can check those out, how to do that. So what I'm going to be giving you is, what am I going to be giving you here? I'm going to be giving you R. I'll give you R of U and V. And it's going to be a three-dimensional surface. That's what these are, parametric surfaces. So there's going to be something X, something I, plus something J, plus something K. And I'll give you the domain in terms of U and V. And then you can calculate the partial with respect to U and the partial with respect to T. Take the cross product, which will give you a vector. But then you take the magnitude of that vector to give you a scalar, and then you'll integrate it. And you'll integrate it with respect to U and V. So this dA part becomes associated with the dA. And yeah, so it just becomes du dv. So this dA part becomes du dv, and then you'll integrate with respect to u and with respect to v. So number 4, surface integrals. So you have to be given some kind of a surface, a parametric surface, and then figure out the surface integral. And this will be, so there's the surface integral with a scalar and the surface integral with a vector. So again, I'm going to tell you what set of problems you're going to be looking at to help you prepare for this. So this is page 1118, 13 through 16. So in this case, it's a surface integral involving a scalar. So you'll be given some f of x, y, and you'll be given some r as a function of u and v. So the surface is parametric. You'll have to parameterize your function there. And now this function is a function of x and y. So if you look at 17 through 22, you've got f of x, y, and z. And if you look at 20 through 28, you've got the flux vector. So I'm just going to test you on this this surface integral stuff. So you can look that over. Number 5 is the divergence theorem. So the divergence theorem is a way of doing a surface integral as a volume integral. And I'm having second thoughts here. I might add an extra problem. So yeah, let's put another problem in there. I haven't done it yet, but as I'm going through here. So let's also do a surface integral here, because we really haven't. Surface integral involving a vector. So this f dot n dot ds. So that's 23 through 28. Let's look at those problems as well. So that'll be problem 7, number 7. Okay, so number 5 is the divergence theorem, page 1127, and 5 through 16. A lot to choose from there. I'm sure we did some of those. So there you're going to instead of doing this, you're going to do the volume integral. So you'll take the, so it's the integral. Actually, this is the divergence theorem. This is, sorry, that's for the previous problem. So the divergence theorem does the integral of f dot n ds. So this is a line integral, and you replace that with the integral over the region. So you'll need to instead of doing the line integral, you do a integral over the region. And then number 6, that's Stokes' theorem. So I'm not going to ask you to verify it. I'm just going to ask you to do it. So Stokes' theorem, again, this 1133, problems 11 through 20. So look those over as well. So that's where you need to concentrate on. And now I'm going to add that extra problem to the test, problem number 7. And like I said, I'm picking problems right out of the book, so you may get lucky, and I don't think they're the ones that I assigned for homework. But the reason I'm picking ones out of the book is so I know that it's not a mistake. I have a solution somewhere or another. So, but you don't know which one I'm picking, so you still have to need to know how to do them.